All right, so to continue with the free energy problem slash paradox, I've stumbled upon an interesting paper that goes way more into detail on how energy is transferred from one object into the other in an elastic collision, because conventional explanations, they always say the same and they don't really go into detail, in a lot of detail. And this paper mainly focuses on the simple fact that when object one collides into object two, that both objects compress a little bit and then reflect energy. There is a compression force and a reflection force, and this is what the main focus is, which is interesting, because it's important. Eventually, the point is that the compression force equals the decompression force, and so the momentum of the compression force equals the decompression force. It should also be conserved, the momentum. So let's take a look. We see here some drawings. We got a yellow sphere, one mass colliding into the blue sphere, the bigger mass. In this case, they are both initially traveling in the same direction, but mass one has a bigger velocity, so it will eventually collide into mass two. And so in the next phase, there is a contact point where they just touch, but not compress yet. And then in the next phase, they start to press into each other. There will be compression. And so both will be exerting forces against each other. Since the yellow sphere is pushing into the blue sphere, that's a force, and vice versa. There's force coming from the blue sphere pressing into the yellow sphere. And then in the next phase, compression continues until it will reach a maximum compression point. And then in the next phase, the reflection parts happened, the reflection phase or the decompression phase. And then they go in opposite direction, but the velocities, of course, will be different. So let me read some of it. Upon impact, forces occur at t beginning, so the beginning point, that will accelerate the blue sphere, decelerate the yellow one, and deform elastically both of them. These forces grow to some maximum coupled to maximum deformation at t maximum. That is an interesting point in time because the two spheres are now as close together as they ever will get and move at exactly the same speed. So that's interesting. At the moment of maximum compression, both objects will move in the same direction with exactly the same speed. That's important to know. For example, if we have a situation where we have two equal masses, 1 kilogram colliding into 1 kilogram. Let's say it's coming in at 10 meters a second. The second one is standing still, 0 meters per second. Then mass one colliding into mass two. They start to compress into each other. The compression phase begins. And so momentum is now being transferred. And the velocity of mass one starts to decrease and the velocity of mass two starts to increase. So the initial velocity was 10. That will become 98765. And the velocity of mass two will become 1, 2, 3, 4, 5, 6, 7, etc. No, it will be just 5. No, it will continue, but it's so we start with 10 and 0, and so it will be 9. So 10, 0, 9, 1, 8, 2, 7, 3, 6, 4, 5, 5. And that will be the equilibrium. At this point, that will be the maximum compression phase. So yeah, mass one is pushing mass two, so they will move in the same direction. And at this point, at the maximum compression point, the same speed, which will be 5 meters per second. Both will be moving in the same direction at 5 meters per second. At the maximum compression phase, but only for a very short little moment, because very soon they will bounce. The second mass will bounce off. The same with the mass one, it will bounce off. They will reflect. And they will reflect with the same force. So there's the compression force and the reflection force that will equal. That's the same. So At the maximum compression force, as you can see here, both are going at 5 meters a second. And then, so the reflection happens with the same force. So mass 2 will gain an extra 5 meters per second, and mass 1 will be reflected with 5 meters per second in the opposite direction. So it was going 5 meters per second in that direction, and now it's being pushed back 5 meters per second in that direction. So we have 5 minus 5 equals 0. So mass 1 will be standing still, and mass 2 already was going at 5 meters per second plus an additional 5 meters per second equals 10 meters per second. So total transfer of energy, we start with 10, 0, and we end up with 0, 10. So that makes sense for equal masses. But then the next case comes where we will deal with 1 kilogram versus 2 kilogram. But let's first check the paper again. Hold on. Right, so there was a small telephone interruption. Let's continue. I was continuing with the text. So we have the diagram of compression and a maximum compression, and then the decompression phase, and then forces and deformations. Right. Yeah, well, so I will link this. It's from a site. No, I will put it in my drive and link my drive link. I will share my drive link. So here we have a couple of equations. So it says the compression force equals the decompression force, and then you can calculate the compression force of both masses, and that will equal the same. And then you can calculate the decompression forces, and that will equal the same. And then another additional equations to calculate the velocities after collision. And then, yeah, the V mid, that's the midpoint speed. That's the speed at which they're going when they reach the maximum compression point. Where is it? This one. So that if you put in the numbers of equal masses, and if you put those numbers into that equation, you will come out with 5 meters per second. All right, so let's now go to the 1 kilogram colliding into 2 kilogram. 1 versus 2. Which one is it? This one. So 1 kilogram comes in at 10 meters per second. 2 kilogram is standing still, 0 meters per second. Then they start to press into each other, compression phase. Velocity of mass 1 is decreasing, velocity of mass 2 is increasing. So then what we want to know is, what is the velocity of both masses when they... Sorry, interruptions. When they, what's the speed going to be when they reach maximum compression point? So when we look at the equation, mass 1 times V1 mv, which is momentum. So you calculate the momentum of mass 1 before collision plus the momentum of mass 2 before collision, and you divide it by both masses summed up, mass 1 plus mass 2. So in this case, mass 1 is 1 kilogram times 10. The velocity is 10 meters per second. So we have 10 plus mass 2, which is 2, plus 0 meters per second, which is 0. So 10 plus 0 is 10, divided by m1 plus m2, which is 2 plus 1 is 3. 10 divided by 3 is 3.33, or 33333, etc. So the velocity will be 3.33 meters per second. At the maximum compression point, they will both move in the same direction at 3.33 meters per second. And we can see here that the momentum is conserved. At this point, we have momentum of 3.33, and momentum of the 2 kilogram is 6.66. Add those together, 3.33 plus 6.66 is 9.9910. Momentum is conserved. Then the reflection, the decompression phase. The reflection phase, and I admit I have some trouble trying to calculate momentum, it doesn't seem to work out. There's a misunderstanding on my part, I believe. So the compression force equals the decompression force. So it's like when it decompresses, when it reflects, we have the 1 kilogram and the 2 kilogram pushing themselves away from each other. So it's like, you can see it in this way. So the 1 kilogram is pushing. So we are in a vacuum. We are in space. There's no gravity. There is no friction. There's no anything. The 1 kilogram is pushing into the 2 kilogram with the same force as the 2 kilogram is pushing into the 1 kilogram. So what will happen? Will the 1 kilogram come out with double the speed? Well, I have a couple of scenarios. Scenario 1. So this is the maximum compression point. Momentum is conserved. They're both moving at 3.33 meters per second. Then when they reflect, according to the equations, the prediction is that the 2 kilogram will eventually come out with 6.66 meters per second. And the 1 kilogram will go in the opposite direction with 3.33 meters per second. So that means that in the reflection phase, the 1 kilogram should bounce back with 6.66 meters per second, because it was initially already going at 3.33 meters per second that way. So it has to bounce off 6.66 meters per second in the other way. Okay, so the 3.33 will first decelerate to 0. At this moment when 0, the momentum is also 0, and then it will continue in the other direction, increasing again to 3.33. All right, so it has to be 6.66 meters per second. The 2 kilogram over here was also already going at 3.33, and now it is being pushed with an additional 3.33. So you have to add them up. Add these, you have to add the compression force with the reflection force, or the velocities. You have to add them, which means 3.33 plus, so for the 1 kilogram, 3.33 plus minus 6.66 equals minus 3.33. The minus sign just means it goes in opposite direction. It's not a negative value. It's actually just positive 3.33 going in opposite direction. It first has to decrease to 0 and then increase to 3.33. All right. The 2 kilogram is 3.33 plus 3.33, 6.66. That's going to be the eventual velocity. That's according to the conventional prediction. 6.66 for the 2 kilogram, 3.33 for the 1 kilogram in opposite direction. But calculate the momentum. So it's 6.66 being pushed back. So momentum is 6.66. And the momentum of 2 kilogram is also 6.66. Add those together and you have 13.33, which is 3.33 extra momentum. So to be honest, I also don't understand this in a theoretical way. It probably still has to do with the negative aspect, that it's going in the opposite direction, but it can't undo, the momentum can't undo itself, right? Sure. So it went in with a momentum of, so at the compression force, at the maximum compression point, the momentum is 3.33. And then it's being pushed back with 6.66 momentum. Somehow, it can be the case that 3.33, yes, sure, it decelerates the velocity, and then at a certain point, it will be 0, the momentum. And then it will start to increase again, the momentum. But, it needed those 6.66 momentums were needed to decelerate the 1 kilogram mass. The 6.66 momentum are needed to decelerate it and to increase it again to 3.33. So it must be 6.66. But then when you add these up, there is extra momentum. Scenario 1. Scenario 2, where we try to calculate if the momentum, where we have, in this scenario, the momentum is also conserved. If you do the math, if you want to do it, if you try to conserve the momentum. So in the previous scenario, 6.66 momentum coming out that way, 6.66 coming out this way. Too much. So if you want to be correct, then the 1 kilogram should come out with only 3.33 meters, 3.33 momentum. But in that case, it should reflect back with only 3.33 meters per second. And if it's already going 3.33 meters per second and it goes back with 3.33 meters per second, then it will equal 0. And that's not what happens. Yet, in this case, the momentum is conserved. But it doesn't make sense because that's not what happened. That's not what happens in an experiment. Scenario 3. Okay, so the 1 kilogram does bounce back with 6.66 meters per second. But if you want to consider the momentum, then the 2 kilograms should only be going at 1.66 meters per second in that direction, such that the momentum is 3.33. Then it will also equal 10. But that's also not what happens, according to conventional predictions. So in this case, the 2 kilogram comes out with 5 meters per second, which should be draft science prediction, 5 meters per second at best, but it's also not the case because the 1 kilogram is also bouncing back. In draft science ideal situation where all energy is transferred, the 1 kilogram should be having 0 velocity. So this is still not resolved. Yet it's interesting because it goes more into detail. It talks specifically about compression force, decompression force, and how actually those momentums should also be conserved. And I don't know what I'm doing wrong. So please enlighten me. I don't understand how momentum is conserved. Right, that's it. That's gonna be this video. It's a rather long video, I guess. Okay.